Hello, friends, and welcome back to the Physics Frontier. In our previous episode, we explored the fascinating journey of Rutherford's experiments with radioactive emissions and his discovery of the proton. Today, we turn the page to another pivotal moment in physics, the discovery of the neutron by James Chadwick, and how this uncharged particle unlocked the power to split the atom and reshape modern science. Stay with us on the Physics Frontier as we continue to explore the remarkable discoveries that shaped the world of physics. How can an atom be split? What weapon could do it? This question sparked investigations everywhere. Following the path indicated by Rutherford, one day, his dedicated student, James Chadwick, made a breakthrough. He discovered the neutron. Little did anyone know that this neutron would one day become the harbinger of devastation, bringing a horrific death to millions in Japan. At that time, the mystery of radioactivity had not yet been fully unraveled. Beyond Rutherford's Cavendish laboratory, researchers around the world were also racing to uncover the secrets of radioactivity. It was 1930 when two German physicists, H. Bothe and Walter Becker, conducted a peculiar experiment. They bombarded beryllium metal with highly energetic radioactive alpha particles and observed the emission of a potent radiation. This radiation was so powerful that it could easily penetrate even a 12 centimeter thick copper sheet. However, they couldn't explain the nature of this mysterious radiation. The findings of Bode and Becker soon reached the leading centers of radioactive research, the Curie Laboratory in Paris and the Cavendish Laboratory in England. Irene Curie and Frederick Joliot replicated the experiment. They observed that when the emitted radiation was directed at paraffin wax, high-energy hydrogen atoms, or protons, were ejected. Since paraffin wax is rich in hydrogen, they concluded that the mysterious radiation was strong enough to knock hydrogen out of the wax. While their experiment was fascinating, their interpretation was flawed. Had they paid closer attention to Rutherford's earlier predictions about the presence of a heavy neutral particle within the atom, made during his Bakerian lecture, they might not have made this mistake. Instead, they classified the unknown radiation as highly energetic gamma rays. They were on the brink of discovering the neutron, but fell short due to this oversight. Meanwhile, Rutherford's student, James Chadwick, had been searching for this neutron for nearly 12 years. He had sensed its existence but could not capture it in experiments. The Curie team's new findings now provided him with a clear direction. By measuring the energy of the protons emitted from paraffin, Chadwick realized that gamma rays could not possibly produce such high-energy hydrogen atoms. This led him to conclude that the radiation from beryllium bombarded by alpha particles was not gamma rays, but a stream of neutral particles, Rutherford's hypothesized neutrons. Chadwick calculated the mass of these particles and found it to be slightly greater than that of a proton. Finally, in 1935, James Chadwick was awarded the Nobel Prize for the discovery of the neutron. But the story doesn't end here. The Curie team continued their groundbreaking work on radioactivity. While natural radioactivity had been understood, the next question was whether radioactive elements could be artificially created. The answer was yes, and it was demonstrated by the Joliot-Curies. In 1934, they bombarded an isotope of aluminum with alpha particles, resulting in the creation of a radioactive phosphorus atom. This phosphorus was unstable and decayed into silicon while emitting radiation. However, this radiation was not alpha, beta, or gamma rays but a new type of particle stream. Using photographic plates and Geiger-Müller counters, Irene and Frederick Joliot confirmed the presence of these particles, later named positrons. Positrons are the antiparticles of electrons, carrying the same mass but an opposite charge. For their groundbreaking discovery of artificial radioactivity, Irene Curie and Frederick Joliot were awarded the Nobel Prize in Chemistry in 1935. In Rome, scientist Enrico Fermi began experiments inspired by the Curie team. However, instead of alpha particles, he used neutrons. Unlike charged particles, neutrons are unaffected by electromagnetic forces, allowing them to penetrate atomic fields more effectively. Fermi bombarded various elements with neutrons. The first 8 attempts failed, but the ninth element, fluorine, did not disappoint. By bombarding fluorine, Fermi successfully induced artificial radioactivity. In his experiments, Fermi made 2 key observations. The radioactivity produced by neutron bombardment was at least 100 times stronger when the neutrons were slowed down using water or paraffin. Bombarding uranium, the heaviest known element, with neutrons created 1 or more artificial uranium elements. While his first observation proved correct and greatly influenced future nuclear research, his second conclusion was flawed. Fermi had unknowingly caused the fission of uranium atoms with neutrons, but this groundbreaking fact was dismissed at the time. Who could believe that a tiny neutron could split a uranium atom, something that could withstand impacts from millions of volts? It seemed as absurd as expecting a ping-pong ball to break down a mighty fortress. Yet truth often takes time to be recognized. In 1938, the Curie team resumed their experiments with neutron bombardment of uranium. They found that the resulting fragments were much lighter than uranium, indicating that the uranium atom was splitting. However, this result puzzled scientists, as the expectation was for uranium to absorb the neutron and transform into a heavier element. Unable to provide a satisfactory explanation, Irene Curie once again missed the opportunity to identify nuclear fission. This was understandable, given the lack of clarity surrounding the atomic nucleus at the time. The Curie team's results were widely doubted, even by Rutherford's own student Otto Hahn. But later that year, Hahn and his colleague Fritz Strassmann repeated the experiment in Berlin and confirmed that neutron bombardment indeed split uranium atoms into smaller ones. Further analysis showed that one of the fragments was barium, a much lighter element than uranium. Hahn's collaborator Lise Meitner and her nephew Otto Frisch analyzed the findings and concluded that the uranium nucleus was splitting into 2 smaller nuclei, a process they named nuclear fission. Enrico Fermi and others later demonstrated that each uranium fission emitted 3 neutrons, which could induce fission in 3 additional uranium nuclei, creating a chain reaction. This rapid process released an immense amount of energy. If left uncontrolled, it could result in an unimaginable explosion, the devastating kind witnessed in Hiroshima and Nagasaki. From artificial radioactivity to the neutron to the unleashing of nuclear fission, these discoveries weren't just scientific milestones, they were turning points in human history. Thanks for being part of this journey into the heart of atomic physics. If you enjoyed this video, be sure to like, share, and subscribe for more science-packed adventures. Until next time, stay curious, stay inspired, and I'll see you in the next episode of the Physics Frontier. Goodbye for now.